Okay, let's go through last year's SAT for the wave section here. You've got a receiving antenna that's got a horizontal orientation, so it's horizontal, and it's going to receive electromagnetic waves produced by a station. You need to state the direction of the plane of polarisation of the waves that are being produced at the station. Now, if it's receiving it in the horizontal orientation there, that's the way the plane of polarisation should be, so it's horizontal. That's also the same direction that the electric field will be going in. Okay? Calculate the wavelength of the television signals then if they're broadcast at this frequency. That's a frequency in megahertz then. And don't forget, radio waves are actually the speed of light, so hook that up there, it'll be 3 by 10 to the 8. So we're trying to find wavelength. So the equation on the formula sheet is this one, B equals F lambda, and you're going to rearrange for lambda for the wavelength there. So lambda is, instead of times by frequency, you're going to divide, so divide by frequency. Now 104.7 is in megahertz, so if you look that up on the formula sheet, it'll be times 10 to the 6. So just use that table on the formula sheet, and if you get that there, we'll get an answer. Okay? And that'll be in metres. So what you've got here is a directed laser pulse going down to the lake. Some reflect off the surface of the lake, some of that penetrates and goes off the bottom. So there's your lake there, and there's the bottom of it. It's going to come down like here, reflect off the surface, and then go in and reflect off the bottom. And we're interested in the time delay between those two beams, because it tells us how long it was underwater for. Okay? Here the delay is 2.58 microseconds for the first one, and 2.92 for the second one, so we need to know that time difference between those two beams. So it's in microseconds. So delta T will be 2.92, the long one, take away the earlier one, and we're doing this in microseconds. Look that up. So that'll tell you the time delay between the two beams. So they've also told you the speed of light in water, you've got to calculate the depth. So the extra distance travelled will be the velocity in water times by that time delay there. And that'll tell you their distance there and back. You have to halve that to get the depth then, because it's only halfway then, half the trip. So divide that by 2. So doing that then, justify the use of a powerful laser in labs. It's really important that you actually get enough of the light energy coming back to read it on the sensor. So you need a powerful laser because of that. And you lose a lot of light there in scattering and absorption. So scattering off the surface of the water here where it spreads, and also off the surface of the actual bed there, and also some absorption due to sediments or particles suspended in the water here rather. So they're the things you're pointing out. You're losing energy due to scattering and also due to absorption, and therefore you need a high beam to ensure there's enough energy coming back. Okay. So here we've got a red laser beam for number 3, illuminating 2 slits there, producing interference pattern. You'll notice it does not need a single slit here because you've already got coherent light in the laser beam, which means it's maintaining a constant phase relationship. So we want to explain why light from a normal incandescent source would not be coherent. Okay? So an incandescent source is very hot, which means you've got a range of vibrations in that particular temperature. You've got a range of vibrating particles at different frequencies. They're going to emit the frequencies of different electromagnetic radiation. So if the frequencies are different, then you're not going to get maintaining a constant phase relationship in those waves. By the way, they're also going to have a range of sources of different phases as well, which is also why you won't get coherence there. So key things to point out here are the atoms vibrate at a range of frequencies. Okay, that's going to cause the EM waves released to have a range of frequencies, and therefore they will not maintain a constant phase relationship. Now the next part says, describe the change you have to make to the apparatus above to maintain a stable interference pattern. Well, you need to get the sodium lamp waves to actually be coherent. So if you add a single slit in front of the pair of doubles there, like that, so add a single slit between the double slits and the sodium light source here, that will ensure that you'll get diffraction going on here, and you get a single point source, and so the waves coming out of these 2 slits will therefore have come from the same original source, be matching and maintain a constant phase relationship. Okay? So you place a single slit in between the double slit and the sodium wave source there. Okay? Explain the bright fringes of the 2-slit interference pattern that we've seen above there. So the bright fringes are a result of constructive interference, so somewhere point that out. And that's occurring when the path difference between the 2 slits is going to be equal to a whole number of wavelengths, allowing them to arrive in phase, giving you that constructive interference. So for any point on the screen, there's a path difference between the 2 slits going to that point on the screen. If it's a whole number of wavelengths, we're going to get them arriving in phase and constructive interference. So key things here are to point out you've got constructive interference giving you the bright bands, and that's when there's a path difference there between the 2 slits and the screen being equal to a whole number of wavelengths, and therefore they're going to arrive in phase. So sometimes you might have to say that in phase pattern, sometimes not, but I would hedge my bets and put all of that in there, those 4 points. Okay? Now this next part says, state the value of the path difference between the two slits at point P. So if you look at point P there, it's actually the second dark band away from the centre. So looking at this here, you would find that this has got a path difference of 0 in the centre from the two different slits. They're going from there and there. They actually travel equal distances to the middle. There'll be a whole wavelength out here. Here will be 2 whole wavelengths out. So the path difference at P will be 1.5 wavelengths. Now here we're being told the distance between the slits, D. Okay? They're telling the screen how far it's positioned away from the slits, so that's L, how far is it to the slits from the screen. And you've also got a diagram here of the fringe separation, which is this delta Y idea. So it says here, using the diagram above, determine the distance between the adjacent maxima, which is called the fringe separation. All right? Mark clear on the diagram the measurements you have used. So you don't want to do it over one pair here, where you've sort of got to guess where the middle is kind of thing, or the edges. You're better off doing it over several. So try and find a matching part of the pattern that's actually matched further down. So if you start from the edge of here, as the start of a red band, you could actually go all the way out to the start of a red band here. And mark that as the distance you're measuring there. Okay, so it's the distance you're going to measure. And delta Y is 5.2 millimetres. Now, that's the total distance. You're going over 1, 2, 3, 4 fringes though. So for one fringe, you're going to divide that by 4. So you're going to get 2.6, 1.3 millimetres, or 1.3 by 10 to the minus 3 metres if you like. So there's your fringe separation, delta Y. The next one says, hence show that the wavelength of the red lines is this. You're trying to find the wavelength now. So the wavelength, there's 2 formulas here involved in this particular arrangement. You can use d sine theta equals m lambda, or that one. Now we're not dealing with the angles here, so you're much better off doing the bottom one there. So you want to use delta Y equals lambda L on D. So if I try that here, we have got all 3 of those things, but not the wavelength. So if we rearrange that for wavelength and bring the D up, it'll be D delta Y, take the L down, and putting that in there, you should get it. So the distance between the slits has been given as 1.55 by 10 to the minus 4. The delta Y, we just worked out to be 1.3 by 10 to the minus 3. And we're going to get a L of 0.3. So that'll tell you the wavelength. And it should be something to minus 7 you'd expect. And in the red end, we're looking at the sort of 7-ish total sort of size, 7 by 10 to the minus 7. Okay. Now the next one says explain the change in separation if you're going to use a green laser beam instead of a red one. So it's just important to realise that the red is the largest wavelengths and it goes down to smaller wavelengths at violet. So green is sort of in between, but definitely the wavelength for green light is going to be smaller than the wavelength for red. So you get smaller wavelength for green light. And because we're using this idea of double slit, because we're using a double slit, delta Y is equal to lambda L on D. Naturally, if you go to a smaller wavelength, you're going to have a smaller fringe separation. So what we're trying to point out here is that the wavelength of green light is smaller than red, and we understand that because these two are proportional like that, the smaller wavelengths will give you a smaller fringe separation, and that's all you need to point out there for the 3 marks. Smaller wavelengths show proportionality, and therefore explain you're going to get a smaller fringe separation. All right. Now then we use a new laser now with the same experimental setup, and it's found that the 3rd order maximum for the new one is the same position as the 2nd order maximum for the original, for the first one you used. And they want you to calculate the wavelength of the new beam. So it's important to realise here that what you've got here is you've got a 3rd order maximum going like that for the fringe separations here. There's the 3rd order maximum there, 1, 2, 3. And that's coinciding with the 2nd order maximum of another one. So that's going to be a bit fatter, it's going to be like that. The 2nd order one's matching up. So what we've got here is a 3rd order fringe separation for the new one, that we don't know, is equaling the 2nd order position for the known one that we actually knew to start with. So how does that let you work out the wavelength? Well, again, you're basing this on proportionality here. These are proportional, so you should be able to say that the 3rd order wavelength here for the new one is equal to 2 times the wavelength of the old one, the original one, which we actually knew. So So to find that wavelength, and obviously you put that step there again and explain that they're proportional. The wavelength of the new one is going to be 2/3 of the original one, which we actually have from the last thing there. Okay? And you get your 4.5 by 10 to the minus 7. Now the next one we're looking at is diffraction grating, so immediately I think we are not going to be using this one here because that's only valid for the double slits. So you've only got the d sine theta formula there that you can use. Okay, so just keep that in mind. The distance L between the things is 0.29 metres from there to there. They've told you the distance between the 0 and first order maximum is y, an unknown value for this distance between the fringes there, or between the maxima there, that's y there. And they've told you the diffraction grating has 300 lines per millimetre. So that's the number of lines per millimetre, it's 300 per millimetre. It'll be 300,000 per metre, so you should convert to metres there. And this one's not drawn to scale, so you can't use that one, but this one is drawn to scale if you check it out. That's actually the distance between these here. Using the scale diagram above this one, calculate the average distance y between the 0 and the first order maxima. So they said average to give you a clue here. They want you to measure from here across to there and then halve it to work out what the average distance is between the 0 and the first order maxima. So I think from memory that distance there is about 12 centimetres if you check it. I think it might be 12.1. So the delta y then would be that 12 centimetres divided by 2. We want half of that. So you're going to look at 6 centimetres here, or about 6 by 10 to the minus 2 metres. Okay, you just have to check that with a ruler. Now the wavelength for laser light used in this experiment is this much. I've told you the wavelength in as well. 6.34 by 10 to the minus 7. Okay, and it says show the expected diffraction angle theta is 11. So you're trying to find theta here. So we're looking at d sine theta is equal to m lambda, where m is going to be equal to 1, first order spectrum, okay? M equals 1. So m is 1 there. So we're just finding theta. So theta will be sine to the minus 1 of m, which is 1, times by wavelength over d. So the wavelength is 6.34 by 10 to the minus 7. The 1 we don't have to worry about. Now that's not d, this here, the study of n. d is equal to 1 over n if you check out the formula sheet. So we have to invert that to as 1 over 300,000. Okay, and if that's 3.33 by 10 to the minus 6. So doing that, you'll get an angle. Now they're going to use a different laser light in this experiment. They're going to tell you the angle. So for the second minima, which is really weird, they normally take it as a maximum for diffraction grating because the minima is so big. But we'll go with this. The angle to the second minima is 18 degrees. We're still using that d is 3.33 slide diffraction grating. That hasn't changed. And they want you to find wavelength of the laser light with this new beam here. Now the m value, if it was the second order maximum, we just would have done m equals 2. But the middle of that big long black band that's in between the maxima there, which is an unusual thing to do, would be, it's a half to the first one, half a wavelength, and it's 1.5 to the second one. So we're going to be using m equals 1.5 here, which is a very strange thing to do in this question. So again, you're going to rearrange sine theta and then lambda here. So to find wavelength, we're just going to divide through by m, where m is 1.5, and don't forget, that should be in degrees. And you'll get a wavelength to the minus 7. Okay? Now the next one says find the highest order image possible for this experimental arrangement. That's going to occur at 90 degrees in either direction. So theta, anything up to 90 degrees would actually be okay, and possible for m. We're trying to find m, and we've got a wavelength and we've got a d here. So what we're going to do is try and find m here for the highest possible maxima. So d sine theta was m lambda could be rearranged for m by just dividing through by wavelength here. And it's a sine of 90, it should be 1. So we're just doing d on lambda really. Okay. So you get 6.8 by 10 minus 7 here for that wavelength. Putting in there, you get 4.85 for the m value. Now that's the highest it could go to if it's all like 90 degrees. So logically then, there's got to be whole numbers. We're going to have m equals 4 as our highest order, which means you get 4 on one side, 4 on the other, and 1 in the middle if you're trying to work out how many total maxima you can get. But this just wants the order, the highest order. The highest order is 4. Now we're now going to pass white light through the grating, describe and explain the first order maximum. So a central one will just be white to the m equals 0. That's just going to be a white one. But the first order one here stretches out to a spectrum because of the fact you've got a mixture of colours and wavelengths. So the first thing to point out is you've got a white light has a mixture of wavelengths. You should also point out that we know that the sine of the angle is proportional to the wavelengths. Naturally, if there's a wavelength of red that's bigger than the wavelength of blue there, we'd expect the angles then to do the same thing. The red angle is going to be bigger than the blue angle and everything else in between there. Okay? So that's why you're going to get a range of angles for the different colours. They're going to spread, and you're getting a spectrum from violet going down to red. Now the last part to do here is this derivation. A laser is passed through a diffraction gradient to a screen that's a long way away. They've drawn these slits as being really big here. Use the diagram here to show that d sine theta is equal to m lambda for the maxa produced. So I'll be doing constructions here first of all, and each of those constructions will be based on the fact that these are going to be equal lengths to the point P on the screen. They're going to form a right angle then. These are parallel pretty much. Okay. That little angle there is going to be theta compared to that, and we've actually got a triangle there then where that's d and that's theta, and this is the extra distance travelled. That's the path difference between one slit and the one below it. Okay. Now looking at that, the sine of theta is opposite over hypotenuse, x over d. So we can say that that's d sine theta. Okay? For this to give you constructive interference at the other end then, you would need to have this arriving at a whole number of wavelengths with that difference there, so that they arrived in phase. So the last few points here to point out are that the path difference between each pair of slits needs to be a whole number of wavelengths. That is, x has to be m lambda, where m is 0, 1, 2 or 3 or whatever. Okay? And so therefore you can link the ideas together then. And the reason for that is you want to be constructive interference. So point that out here to give constructive interference. So there's another mark for that. And therefore the path difference d sine theta must equal m lambda to get that constructive interference. So there's the other things you need to point out. Okay, thanks.